Hello and welcome to NPTEL online certification course on CMOS digital VLSI design. We are starting a new sort of a chapter and a module today which is basically clocking strategies for sequential design part 1. So, this is module number 1 for understanding the clocking strategies. Now, as we have seen in our previous modules that all your design per se when you are doing a sequential design was all clock driven, which means that your design has to be synchronous with the clock, which means that when for example, if you are doing an edge triggered design, then with the rising edge of the clock you should be able to sample the data and accept the data for evaluation, right. So, it is very important and critical to know what are the various problems of clocking and how a clocking can be applied to a sequential logic for the best performance output. To do that, that is the whole idea behind these two modules which we will be handling over the next few lectures. So, the topic or the outline which we will be handling in this module are, we will be looking into obviously introduce to you subject of the clocking strategy. We will look at the various nomenclatures which people follow in sequential design. Then we will look into the sequential your synchronous design techniques, what are the various synchronous design techniques. We will understand what do you mean by clock skew and clock jitter. So, these two understanding has to be there, right. So, clock skew and clock jitter, what is the difference between them, what do you mean by them and how does it affect your sequential logic flow. So, therefore, that is the fifth part which tells me that if you have a clock skew or a clock jitter, how does it influence my performance of the sequential logic, right. What are the sources therefore of skew and jitter, and therefore, if you know the sources you should find out the techniques for reducing the skew and jitter. So, that is also a part of the issue, and as a part of it we should therefore know how you need to distribute the clock across the chip. So, you should be able to do that in a much proper fashion. Then what are the advantages of synchronous design, that we will be actually revising time and again as we move across in this system and around this area, and then finally we will be recapitulating the whole design flow. That is the general trend which we will be following for this module as far as clocking strategy is concerned. If you remember when we were discussing clocking strategies, we were actually telling to you, we were actually discussing that, or it was discussed to you that during the rising edge. So, what I am trying to tell you is, let us suppose I have a clock here, right, and every rising edge of the clock you are sampling the data. So, I have an input here, and at this edge of the rising edge of the clock my data is sampled, let us suppose, and then it falls here and again rising edge is there. The next sampling can only take place at this point only, right. So, you have to be very cautious that since the data is always synchronous with respect to clock in a synchronous design, at least of a sequential logic, you have to be very cautious that the data is available before the rising edge of the clock setup time as I discussed with you, and should remain like that after the passing of the positive edge, which is basically the hold statement which is there with you. So, these has to be always available to you in all sense, right, and therefore, it should not violate the setup time nor the hold time, that is sacrosanct, you cannot do that, right. So, with this what we will try to do is, we will give you what is the meaning of synchronous design as far as sequential logics are concerned. As you can see, therefore, all sequential circuits have well defined switching events, right. And we have also discussed, what do you mean by switching events? Switching event means that if an inverter switches on and tries to pull a node to 0 or to ground, then that event is known as a switching event. So, let us discuss what is a switching event. A switching event is an event defined as the event wherein you are able to switch an output node either to 0 or to ground, and you are able to sustain that for a longer duration of time, right. Then you have to also ensure that this switching which is happening has to be at a very fast pace, because then only you will be able to allow the data to come inside picture. But then the advantage which comes to you as compared to the previous case is that since your clock, since it is clock driven, Therefore, you have to wait till the next rising edge of the clock in case of a single edge positive edge triggered or even negative edge triggered. You have to wait till the next rising or the falling edge of the clock in order to evaluate that sample, right, and that is the basic issue, right. So, you do not have to therefore speeden up unnecessarily at certain issues, because if you want to speed up, you very well know that you will be consuming more power, and therefore, the power dissipation issues will be typically very large in that case. Now, the systematic switching has to be there to ensure that the circuit is functionally correct, right. Unlike in combinational logic, if you remember, in sequential logic you also have feedback paths, right, and in the feedback path the time taken for the feedback to appear at the input side might be varying, right. It might even come after the clock edge has passed. So, you have to wait till the next positive edge of the clock to come for it to couple itself. So, you have to be very cautious how much amount of delay you should insert into the feedback path for exact matching between the data and the clock. But then if you allow all this systematic switching, you have to ensure that the functionality of the switch or the circuit is not compromised, right. So, functionality is still there, which you should be there. What is it? There are two approaches, there are actually 4 approaches, but we will discuss only 2 here. The first one is a synchronous approach. Or what does it mean? That all the circuit elements will be simultaneously updated with a global clock. So, you have a global clock, clocks are generally off chip because activity factor is 1, and therefore, they are very power hungry, and therefore, you can't afford to keep them on chip for most practical purposes, and therefore, you route through long interconnects from clock to the these sequential logics, right. Now, periodically the global clock will update the data flow through a system, right, and therefore, you have to be very cautious that when therefore, generally for most practical purposes we try to extract the clock from a single global clock. So, maybe I have a single 555 astable multivibrator, and from there the clock is being generated, and I try to extract clock from there itself, right, and using long interconnects we try to send it to the data to drive these sequential logics. In a synchronous design, synchronous basically meaning that your data is synchronous with the clock. The functionality is to ensure that the constraints of the clock generation and proper distribution, that means the constraint of setup time and hold time, as well as how you are distributing the clock in a spatial domain. These are the 2 very important parts to ensure that system or the chip is working properly or not, right, and they ensure, these 2 things ensure the clock generation or ensure the functionality of the chip. This is asynchronous design, wherein there is no global clock required. So, you do not require any global clock. However, the cost you pay for it is that the complexity is very large, right. So, for all practical purposes in this lecture at least, or in this module at least, we will be restricting ourselves to synchronous design only, right. You can have synchronous design. Now, you can have such type of clocks. I will give you an example. You can have a clock in which there are 2 clocks, let us suppose T1 and T2. They are perfectly like they are coming like this. So, their peak to peak is exactly the same, but there might be a case that T1 and T2 might be phase differed by certain values, right. Its clock, so you something like this you get, which means that not only its pulse width is different, but its phase is also different, right, and though they are maintaining the constant phase difference, because this is also, let us assume this to be true, then they are maintaining exactly the same clock phase difference, but they are not exactly the same clock, which means that there is a difference between this clock, right, and exactly if I say this clock, right. So, they are 2 exactly the same clocks, but if I have, so this is T1 exactly equals to T2, but if I have a clock something like this and I have a clock which is something like this, right, something like this, right, then it is differing in phase because the rising edge are not properly matched, and as a result what might happen is that there is a phase difference between the 2, and that might result in small changes in the logic design, right, the sequential logic design itself. So, we do have certain other other methods of doing it. We will not go into details of this one. They are most often used in communication systems, you use it, right, and so we will not go into details of this one in any further details. So, we have understood what is a synchronous design. We have understood what is asynchronous design and how they are different from each other, and how is it that they will be utilized for all practical purposes. Let us look at the synchronous design technique, right. As I discussed with you, we will have the same frequency as the global clock, local clock. A synchronous signal is the output signal, which is you are giving as the data, is the one which has the exact same frequency as the local clock. So, you have a local clock driver which will drive the system, and therefore, your synchronous signal will be one that will have same frequency as the local clock and will maintain a fixed phase offset with respect to the local clock, which means that your data train synchronous signal should be synchronous with the clock, means they should maintain a fixed phase offset with the synchronous clock, right. And yeah, as long as it is able to maintain that, there is no problem in functionality. So, if you look at the second point, in such a timing methodology, signal is synchronized. This is very important, right. Which signal? The signal which you are sending as a data has to be synchronized with respect to the clock. So, it can't happen that you can go on increasing the clock frequency and your data is coming at a much lower frequency, that won't work, right. You have to match the frequency as well as phase. You are allowed to do a offset in the phase, but that offset in the phase has to be constant across the time domain and across the frequency domain, right. That is pretty important, that you should have the same offset available to you for all the values of input signal. So, with the clock, therefore, the data can be sampled directly, as I discussed with you. We have already seen it time and again that there is no requirement for that. So, you see here, if you look at this diagram which you see, this methodology, this is the methodology which people use 90% of its time, right, and that is the standard methodology which people use for a longer duration of time, right. The methodology is something like this. So, you have a register here which is register number 1, right, you have register number 2, and you have a logical block here which is register, which is basically trying to just a minute, I will just yes. So, you have a logical block here. So, in most of the cases which we will be studying in sequential logic design, you will have two registers, one input register, one output register, and there will be some logical block here. It might be a combinational logical block also, for example an AND gate or whatever. We can have also a simple register built within this logical block as such, and you have a clock. So, you see, please see that I am deriving the same clock and feeding it to shift register 1 and to 2, right. So, what I am doing is I am deriving from the same clock two signals going to shift register 1 and 2, which effectively means that whenever there is a rising edge coming at shift register 1, a rising edge will also appear at shift register 2. When there is a falling edge at shift register 1, there will be also a falling edge at shift register 2, fine. But please understand that this logical block will give some amount of a delay, right, because whenever a signal, for example, I am giving an input here, right, in the rising edge of the clock, let us assume that it is a positive edge triggered. So, let me say this is edge triggered. So, I have got an edge triggered here, I have also edge triggered here, and this is positive edge triggered. So, there is no circle here. So, I have an input, and in the positive edge of the cycle this input goes high, and therefore, this register is able to put it into this C in value here, and it has, and then when the positive edge cycle of the clock has passed, the register is all in the non-transparent state, and therefore, the C in has to travel through logical block here, reach C out here, right, will reach C out here, and has to be ready before the setup time of shift register 2, rising edge of the clock, second rising edge of the clock of shift register 2, and then it will be able to give the output. As I discussed with you in the previous turn, there is no direct connectivity as of now between input and output, because these two registers are though working together, but they will be non-transparent during the phase when your when the clock is not in the low to high or high to low, assuming that they are edge triggered design which is available to you. So, this is what I wanted to discuss as far as the basic fundamental block of any sequential logical block is available to you, right. So, this is a basic sequential logical block which you see, and this works fine. This idea or concept is with the concept that this is with the concept that your clocks are perfectly okay and there is no clock movement between this point and this point. which means that let us suppose this interconnect length is very large, right, and there is some problem with the clock moving from this point to this point, then your sequential design is in a problem, because then the rising edge of this and this is never synchronized with respect to each other. For shift register number 1 and 2, the rising edge are not synchronized. As a result, the output will always be lagging behind, and there will be a chance that you might have some problem available to you, right. So when you are trying to insert data between clock and the input and output register, you have to ensure that they are always available or available for evaluation at least one setup time before the clock register, right. So this is what we have learned just now, and we have explained to you what I am trying to say. We will discuss about synchronous timing issues, basic timing issues here, and we will not go into details of this one. If you remember, we have already discussed with you what is known as setup time and hold time. So setup time is the basic minimum time before the rising edge of the clock, right, when your data should be remaining stable, and hold time is basically the time after the rising edge of the clock when your data should be stable for proper evaluation of the data or proper sampling of the data, right. So this much amount of time you have to give, whatever you want to do it you can do it, but this is the amount of time which you have to give it. This gives you a restriction on the total frequency of a sequential logic flow, right. Let me give you the basics ones first of all. So TCQ, which you see the second one, TCQ is basically the maximum delay of the register. This I define as the maximum delay of the register. We also define maximum delay means from input of the register to the output of the register. The delay between those two is basically defined as the TCQ delay, right, C to Q delay, right, TCQ write down. T logic is basically the combinational logical block delay, because this will be composed of certain logical block cells, and the delay associated with that will be basically defined as the T logic delay, right, T logic delay will be defined. So T logic is that maximum delay which is available to you. Please be very careful that in combinational logic block, maybe we will discuss it later on, that there might be certain. So how do you define your maximum delay? You delay across the path where you have the critical path. So you have to first understand what is the critical path in a combinational logical block, and then across that critical path the total delay associated with that is basically defined as by T logic or maximum delay of combinational logical block, right. We have therefore TC clock 1 and TC clock 2, these are the positions of the rising edges of clock 1 and clock 2. So I have two clocks, clock 1 and clock 2, TC clock 1 and TC clock 2 are basically the rising edges of these two clocks, right, and they will be working on these areas to a larger extent. So with this I will stop here today. Next turn we will take up the synchronous timing basics, and then we will look at the various clocking strategies of sequential logic design. Thank you very much.